You have already learned out. I am a lecturer and researcher at the Transylvania University of Brasov, and I also collaborate with Intech Engineering Services, which also operates in the same city. What you'll hear today, so the report, the work that is reported today is a continuation and improvement of a system which we have been working on for the past almost 18 months. And the first version of the system has been presented last year. And now we report on the latest changes and improvements. First, I'll start with presenting some basic cryptographic concepts so that the presentation is readily accessible for anyone. So, as you know, in cryptography there are several developments, and in general, if you speak about classic cryptography, we know about symmetric encryption schemes and asymmetric encryption schemes. Symmetric encryption schemes use the same keys both for encrypting and decrypting the messages, while asymmetric schemes use a pair of public and private keys. The best example in this category, the one that is the most used in everyone's daily lives is the HTTPS system, which is used to access websites securely. We have a public key which which can be accessed by anyone through the browser, and the information that is being sent to the server is authenticated at the other side with the private key. What we have been doing for the past months, we have been looking for a modality to perform computations over encrypted data. So our goal is to perform computations over encrypted data. And we work with two main concepts. We work with sums, and we also work with products. Why sums and products? Because these two can be translated with two basic logical gates, which are known from computer architecture and from Boolean algebra. They are exclusive OR and AND. As you can see here, sums can be assimilated to exclusive ORs, and products can be assimilated to AND. If we, in principle, if we speak about systems that support the computation of sums and products over encrypted data, then we can speak about conducting processing operations over encrypted data without the need to decrypt this data. The applications are obvious. So nowadays it is it is a must to ensure that personal data is being processed and stored in a private fashion, in a secure fashion. So this kind of an approach is fairly useful in in practice. Nevertheless, homomorphic encryption has been a very difficult topic for years. Up until in 2008, Craig Gentry has worked on this topic for his PhD thesis. And he proposed basically the first fully homomorphic encryption model that he was able to use in some real-world scenarios. Basically, what mathematical models can we use? Well, maybe we can use polynomials, or we can use matrices, or we may use basic integers to perform the calculations. In practice, all these are possible and can be used. In practice, the homomorphic encryption is fairly resource intensive, because any encryption operation and decryption involves the existence of the so-called noise. And if the quantity of the noise goes beyond a certain threshold, then decryption is either not possible, or the decrypted message does not coincide with the original one. So it's one of the main goals to keep the noise at the lowest possible levels, and we'll see soon how we approach this in the system that we report. Basically, just as a proof of concept, if we were to encrypt a bit B, then we can choose a large multiple of P. So we have the product Q times P. Then we choose a preferably random small number, which is 2 times R plus B, which is even if B is 0 and odd if B is 1. Then we may have a ciphertext that has this form: Q times P plus 2 times R plus B. And we can apply the decryption in order to obtain the original message, and the noise can be seen as 2 times R plus B. Now, there are categories of brute force attacks that can be applied in order to recover the original text. If there is no noise, then recovering the original text is easier, and the noise makes it more difficult to do so. But as you see, when the noise increases, we speak about the impossibility to obtain the original text, or the original text cannot be obtained in an accurate fashion. So several approaches have been proposed in order to address this issue. One of the models, so I will try to go faster over these theoretical facts and focus more on what is interesting for the presentation of the system itself. From a historical perspective, the initial point was when we applied standard encryption schemes like RSA and so on. And in the case of these schemes, what we were doing was just to encrypt plain text data, and then we were deciphering the encrypted text in order to obtain the full text data. But as I said, we would like to also be able to perform computations directly over the encrypted data. So nowadays, with the exception of a few other contributions, we can use some almost fully homomorphic encryption schemes. And the mechanism of bootstrapping is the one which ensures that the noise, which I talked about in the previous slides, does not increase over the critical threshold, so that the original message doesn't become impossible to decipher. So what this means, the idea is simple. If we have an initial level for the noise, in homomorphic encryption in general, every multiplication increases the noise by 4 times, and any addition operation increases the noise by 2 times. So multiplications are the most, let's say, dangerous in respect to the level of the noise. So during the process through which our algorithm is run, the level increases. And if we attain that level and overcome it, then we won't be able to get the original results in an accurate manner. So somewhere in between, we set up a threshold, and we work on the level of the noise in order to make sure that it doesn't go over the undesired level. So this is basically the bootstrapping method. And every time a homomorphic encryption algorithm is designed, this correction that is applied to the level of the noise should be applied in a continuous fashion. Every time a multiplication occurs, the level increases, and then we have to apply proper measures in order to decrease it without compromising, of course, the outcome of the result. So this was the original point which we considered when starting to work on our algorithm and on the system that we implemented. So the goal is to reduce the noise while being able to perform computations over encrypted data. And what could be a solution in order to address this problem? Well, together with one of my colleagues, we have been working on this problematic, and we have created a model which has been initially reported in a paper that is published last year in IBM Journal. And the improvement that I report for this presentation represents the continuation of that work. Basically, we speak about a medical system. The medical system uses the data that is collected from the patients, while those patients wear some watches which have sensors for heartbeat and related physiologic parameters. The data that is collected is then sent over to the user's smartphones through Bluetooth, and then the smartphones send the data using the data connection of the device to the backend. You will see in an instance what is the architecture of the system. Okay. Right from the beginning, I can tell you that from the literature review work that we conducted, this is one of the few systems which allow for the medical data to be collected safely, to be transported in an encrypted fashion to the backend, and to be processed also in encrypted fashion without disclosing the identity of the patient. The backend is deployed in the cloud infrastructure, in this case in the cloud infrastructure of IBM, but it can also be deployed in any cloud infrastructure which supports services like relational or NoSQL databases, and the ability to run the backend as it stands. So the architecture is the one that is being displayed in this picture. This is the end user, and you see that we have two paths for the data transmission. Why this? Because sometimes we have noticed from our experiments that sometimes it is useful to just send the data from the backend to the user, and from the user to the backend without processing it, and sometimes the data should be modified through some processing. So this is why we have made this separation between the processing and the raw data transmission paths. You see that for the simple transmission path we use a standard AES scheme, encryption scheme, and then for the data processing path we use the fully homomorphic encryption scheme that I am talking about. As features of the system, it supports all four stages of the data processing that one may think of: data collection, transmission, storage, and of course data processing at the backend side. As I said, data collection is performed through the wearables that the patients wear, and the transmission is being conducted by the mobile devices of the users through their data connection. If the data connection is not available, then the data that is being collected is cached locally, and then it is offloaded as soon as the data connection becomes available. Okay, so the fully homomorphic encryption computations are performed in this case using Apache Spark which which allows us to do the required parallel computations that are necessary in the case of fully homomorphic encryption processing. Okay, so we have been talking about the basic operations which a fully homomorphic encryption system supports. They were multiplications and additions. But as I have already mentioned, using only multiplications and additions determines the ever-increasing level of the noise. So at one point, fairly soon, we will notice that we are unable to get back our plain text data. Therefore, we introduced in our system two more operations. These are homomorphic rotate, which basically allows us to rotate the bits of the data in such a way that the level of the noise is kept to a normal level, so not to reach the threshold. And as we may understand, applying this kind of operation may and will produce alterations to the original data. So the fourth operation ensures that this kind of alteration is not possible in reality. What would mean this for a real-world system? For example, as we were able to see in the case of the medical system that I am speaking about, we had cases during our experiments when we got the diagnosis for a patient that he or she suffers from the delayed repolarization health syndrome, which is a medical condition of the heart. And this diagnosis has been associated to another patient because the data has been altered by the homomorphic rotate. But applying the select allows us to overcome this problem. And the level L is the parameter which is very important in the context of the noise. This basically computes the value of the noise, and it is the one which we consider when we work with this noise. This is another more technical scheme that reflects the two data paths that you have seen in the previous channel. For the data transmission and data computation, okay. In plain words, after the data is being gathered from the patients through their wearables, as I said, it's being sent to the user's smartphone through Bluetooth, and then over to the backend using the data connection of the device. At the backend side, we apply the proper fully homomorphic encryption computations. So the four operations: multiplications, additions, select, and rotations. And by applying these operations, we obtain the results in the encrypted form. Then when, let's say, a user wants to know, according to the data which his wearable collects, uh, am I suffering from the delayed repolarization syndrome? He sends a request to the backend. This request is being received, is being homomorphically processed, and then the result is sent also in the encrypted form back to the user's smartphone, which actually performs the final decryption and offers the result to the user. So only the user can see the plain text data that pertains to his or her health state. Another novelty of the system that we report is the usage of the n-true approach. The n-true approach, in short, is a lattice-based approach which has two main advantages. One of the advantages, in practice, it seems that it's being said that it's impossible to be broken by quantum-based attacks. Well, considering the ever-evolving field of quantum computers, we'll see if this assertion holds. But at the moment, what we say, what we know from the literature and from the experiments that were made, it's practically impossible to be broken by a quantum-based attack. And the second approach is the one that it's a faster. It's faster than most of the existing similar approaches. So this allowed us, we incorporated this into our system and allowed us to obtain a fairly efficient utilization of the resources. When I say resources, I have, in my view, several layers. There is the mobile device of the user, which receives the data from the wearables that the patient holds on their hands. It's then the bandwidth that is being used to send the data from the mobile devices to the cloud backend. And of course, there is the cloud backend which performs the actual computation. And although it is more efficient, speaking about a homomorphic system, it is still fairly resource intensive. So any improvement is more than welcome. We have definitely tested the performance and the real-world behavior of the system using relevant metrics. Naturally, we had in mind the level L, and we have tested whether the value of this level L is kept to an optimal level, as it should be, applying the select and the rotation operations, which I mentioned. And then we have another parameter which we have named NCT, which basically represents the encryption of the cardiac rhythm data which is collected by the wearables during the field testing that we performed. As we'll see in an instant, um, we have been basically measuring three categories of medical conditions, and the system was able to produce the results, the expected results in any of the considered situations. And also we didn't have any situation when the data has not been properly assigned to its respective holder. One other remark regarding the usefulness of homomorphic encryption in real-world use cases is given by the fact that, for example, we should think about the CPU vulnerabilities which have started, for example, with the Spectre and with Meltdown, and have continued with other such low-level vulnerabilities of the CPUs. In cloud environments, regardless of how safe are these cloud environments, if such vulnerability exists and a talented hacker will have access to that cloud, he would be able to read other users' data in the cloud without the consent of their owner. So this is another real-world use case which justifies the usage of a mechanism like homomorphic encryption. So one of the parameters that were taken into account is the average heart rate that has been registered at the patients. Okay, I won't go very much into details because I don't want to make the presentation very complicated, but we can discuss if you want with those that are interested. Then the other medical condition is the delayed repolarization of the heart syndrome. This is a ventricular condition that is generated by the inability of the heart's mechanisms to properly ensure the electrical signals are being passed for the in order for the blood flow to occur correctly in the four chambers of the heart. And these patients, although their electrocardiograms turn out perfectly, they suffer sudden death if the condition is not known. And we have used at the core of our algorithm, we have been using this equation. The 475 milliseconds that you see there is the threshold which is indicative of the way that the delayed repolarization, electrical repolarization occurs in the patient's heart. Okay. So basically, just to offer you a glimpse on how the homomorphic process occurs in this case, the cardiac rim data is collected for the given patient. It is being sent to the backend. The backend performs the computation, and then at the patient's request, the results are being sent back to the user's smartphone. The result is in the form of an array of bits, and if in this array of bits it's at least one bit of 1, then the occurrence of this syndrome has appeared with a high probability at least once. Okay. And the behavior that we expected also appeared in all the other scenarios and medical conditions that we have taken into considerations. We have also tested the performance and the behavior concerning the execution time and the utilization of the computing resources of the system. In this respect, we have been using a series of metrics, which we'll see in a moment. But before speaking about the metrics, I'll give you some brief remarks regarding the hardware and the study population. The study population refers to 500 residents of Brașov city, Romania, and the hardware that is of interest, so the wearables, are the Polar H7 watches. It's an improper word, but let's call them watches. Because we have determined them to be the most accurate for our needs. Performance metrics that we considered. The first one is the amount of the data that is sent over to the backend and the amount of the data that the backend sends over to the client devices. This XFAIR thing is a jargon from the networking scope, which basically means transfer. So this is why we have also used this naming convention. Then the storage ratio is a metric which represents the amount of bits that are necessary for in the fully homomorphic encryption system to process and store 1 bit of plain text data. Then we have processing speed, which takes into account the amount of time that is required for the data to circulate from the client devices to the backend, and also the time that is being used for the data processing at the backend. NCT is the number of the ciphertext. Let us recall that this NCT parameter refers to the number of bits that we use to encrypt the data that is being gathered by the wearables. And finally, but not the least important for sure, is the level L, which takes care of the noise. And we have chosen several types of granularities for the data collection. So every 1 minute, every 5 minutes, and so on. In these conditions, we can see that for the most frequent data collection interval, which is every 1 minute, we have almost 3 3 terabytes of data that are being sent from the backend, from the cloud backend to the client devices. And there are 4 gigabytes of data that are being sent in the other direction. While this may seem a large number, and it is a large number, that's for sure, considering the world of homomorphic encryption applications, it is a reasonable figure. And then you can see that all the other parameters scale well with the frequency of the data collection interval. And these are the values for the delayed repolarization of the heart syndrome, which also prove that the approach is feasible in practice. So, just to wrap up the presentation, what we intended to do from the first instance was to prove that regardless of the complexity and the sensitivity of the data, it is possible to collect, store, and process it in a completely secure fashion without giving away the identity of the owner. And we have basically proved that using the fairly consistent sample of 500 people, that such an approach is scalable and feasible in practice. So this is all. If you have questions.
All right, thank you so much, Razvan. So we have 2 questions. Sorry, the first question was this guy. The second is Maxim, so you can give him the mic. But we will take the first one, Maxim here.
Hello. Let's say we all use health system application or mobile, and the application are like global, not just 500 person. Will be the performance affected given that, I don't know, 1 million people are sending health data to cloud system?
The performance will certainly be affected given such a large deployment, but considering proper sizing of the processing infrastructure, then it is still possible to deploy a system that will sustain this kind of large data processing job. So it will be affected, no doubts, but this doesn't mean it cannot be applied. It's still that homomorphic encryption is still a niche topic, and people and practitioners in industry are not much aware of its usefulness.
Okay, thank you very much.
Please, Maxim.
Okay, so you are integrating a neutral crypto system, yes, and TRU. Are you using the NIST standard, or you modified it?
So we haven't integrated the proper quantum computing into our system. Is only that N-true.
Yes, I'm talking about N-true.
Yeah.
Are you using NIST standard, or you changed something?
Basically, we use the model that is being defined by the creators of N-true, and we applied some modifications which we noticed that induce some performance speed-ups.
It's interesting to check it because
in practice.
Yes, because NIST has its own standard. Yes, according to it, so it must be double-checked. Yes. Mm-hmm. Okay, thank you. Mm-hmm.
Yeah.
Hi. I have a double question. Maybe you can use for future development of this project. First, Polar H7. What kind of sensor does it use? PPG or ECG?
Who?
What kind of sensor does it use? PPG or ECG for heart rate detection?
We use the standard Polar H7.
You don't know what the sensor is. If it's a PPG, you can have distorted data. I mean, I'm wearing a XAMI device and it has a PPG and it's not perfect, but the ECG sensor is more accurate.
We didn't make, we really, honestly, we didn't make this
Take a look on this sensor.
separation.
It might help you. And,
It's just the standard Polar H7.
I don't know
We didn't make a research into the hardware features of the sensor.
Okay. And the second question would be, okay, all this encryption, everything new, but the flaw is at the beginning, the transmission between the wearable and the device. It's Bluetooth, it's hackable. You can get that data, raw data, and interpret it as
Yes,
you want.
if you have an attacker which is really in
30 meters in
Yes.
plain sight.
this is the only
It's an issue.
section of the transmission channel that may pose issues.
Okay.
Indeed, but in practice, probability is low.
Yeah, if there is intent.
Yeah, I agree. I agree, but
Okay, that's all.
Do we have other questions? Aha, yeah. One more, okay? Thanks.
Hi, thank you for the presentation, by the way, it was really cool. I'm a bit curious about the detection rule, for example, the one for DHRS, DRHS, sorry. Can you tell me if it was written as a proof of concept, or is it false positive proof?
as a false positive proof, what
Yeah.
what do you mean by this?
I mean, if you take that rule and you apply it in a real life scenario, like, for example, on a watch which is wear by somebody right now, would it detect with an accuracy of 100%, or is it just a POC rule, a proof of concept rule, written exactly just to demonstrate that the
What I can
system,
tell you,
the backend is
yeah. In that sample of 500 patients, we are sure that 11 of the patients were actually suffering from this medical condition, which has been confirmed by their medical practitioner, and we have got the positive result that these patients indeed are being detected as such by the system. So, considering the data that we gathered, it's a prototype that does the job, basically. I'm not sure if I covered.
Sorry, I was just thinking, for example, out of those 500 people,
Okay.
did other people die and were not detected by the detection rule?
Fortunately, none of them died yet, but
I mean, I know it sounds awful, but this is how you actually test the false positive rate to see how effective it is in practice. Somebody's got to die.
I understand what you say. Yeah. Now I fully understand what you say. So we did the experiments as they currently stand allowed us to prove that the 11 patients which were medically attested as suffering from these conditions were reported as such by the system. But regarding the false positives, in the sense that you say, we still don't know. There is still work to be done.
Okay. Thank you so much, Razvan.
Thank you.
Thank you.